Today we are going to start doing a little bit more math associated with thermo and start our process of kind of rederiving rigorously all of the functions and terms that we will be using to calculate fluid properties, right? The challenge of thermo is estimating fluid properties, not sort of in applying the energy and entropy balances. But with that being said, we were going to start off with energy and entropy balances, going over again one more time how we actually use them to solve real processes. So I'll do this for energy, but it's really basically exactly the same procedure for the entropy balance. So the full form of the energy balance that we like to start off with in chemical engineering is this one here. So the change in energy of the system with respect to time is going to be equal to how much energy enters the system in the form of enthalpy. So we can put subscripts here, but if you see the summation, right, just sort of implicitly, those subscripts should be there, plus the rate of energy in or out from heat, plus the rate of energy in or out from work. Now you can think of this as shaft work, and also we could do P dV dt. This is if it's a constant pressure. So generally, what that means is we can have an arbitrary number of streams coming in or out of a process. The way that this has been drawn, we have heat entering, we have shaft work entering, so positive work is going into the system. But again, this can be a convention that can be changed quite readily. And then lastly, due to this PdV term, right, this is a work term as well, that means that here the volume is not constant. So this is something that we'll see most often when we do the generalized piston cylinder type devices, but in a real process you obviously want to avoid the system expanding and contracting. Right? So maybe for a benchtop scale thing you can pop a balloon on it or something so that it could expand and contract. But in a very, very large scale process where you're processing millions of tons of material, it's best to have rigid walls. So this is our general energy balance equation. So we'll talk about a couple of quick assumptions or simplifications. Let's say we have a closed, rigid system. What do we cancel out in a closed, rigid system here? Mass goes away, and PV expansion goes away. So in that case, we have the change in internal energy of the system is only equal to how much energy is entering or leaving the system in the form of work or in the form of heat. So how we would write this then if we wanted to solve for the, let's say, heat, for example. What we would do is we would integrate this from state 1 to state 2. That's really the power of a state function of thermodynamics, is we don't have to really define how we're doing that. We know what the initial conditions are, we know what the final conditions are. And most generally, we want to set up all of our problems where we don't care about how it gets from point A to point B. We just know that it gets there. So this is the case then. If I integrate du, so the change in internal energy with respect to time from state 1 to state 2, this is what it means. That's it. Right, so the calculus in thermodynamics is very fun. It's really easy. You integrate it, done. This is also equal to what we call delta U. And in this case, because it's time dependent, we can kind of think of this as final minus initial. This is what the delta represents. This hopefully shouldn't be shockingly new nomenclature. And in this case, we notice there's no dots here. That's because it's not the rate of energy in the form of heat or work, but it's the total amount of energy in, right? So if we were given a piston cylinder problem and it was water and you had the steam tables, all we would need to do to figure out how any of this worked is that at state 1, it would be at some temperature pressure condition. At state 2, it would be at some temperature pressure condition. All you would do is go to the steam tables, look up what the internal energy of water was at that condition, and plug it into this equation. So obviously here, we would have to either have it be adiabatic or constant volume or no shaft work, right? Because there's 3 variables. Whatever the case is, let's say this is an adiabatic system with an impeller, and the impeller is heating up the fluid inside of a closed system. Let's say it heats up, 50 degrees Celsius. We could figure out how much work it would have taken to do that. That's just one example problem to come up with. Yes?
Would it be wrong to think about it as so we have a known fixed time range, and that's why we know the amount of energy?
Well, it actually, so it gets a little bit into what we're talking about today. It actually does matter a little bit, the time range. In fact, it has to be infinitely long. Okay. Otherwise, it's an irreversible process. But in general, we're going to assume that it just happens, and then it happens over a reasonable time period. But in actuality, in any real thermodynamic calculation, we actually have to do this over an infinitely slow time. Otherwise, we'd have the creation of entropy, and we'd have to keep track of the rate of entropy generation. And we will talk about that today. We'll derive why doing things fast causes more entropy to be generated.
So this equation doesn't apply for small time ranges?
No, it applies for everything.
Okay.
So this equation applies regardless of how long it takes to do something. So this could happen very quickly, it could happen very slowly. For an energy balance, A-OK doesn't matter.
Okay.
Now, if you're doing extracting PV work here, then it really does matter the path and the time, right? Because work is not a state function. So if we are doing the classic piston cylinder device, in this case here, this isn't shaft work. Let's say this is a PV work, so this is a minus P delta V, right? So that would be volume expansion work, which kind of transitions us a little bit into something else. But so if I wanted to extract, right, this is, let's say, a high temperature, high pressure fluid inside of a piston cylinder device, which is exactly like what you'd have at a power plant. And you want to expand it in just the right way to extract the most power out of it. We want to do it very, very slowly. If we do it really quickly, we'll actually get less energy out of the system because we'll be generating a lot of entropy.
Okay.
But in order to do things what they call reversibly, where you don't generate entropy, and when you generate entropy, you waste work, you generate heat, that's what you have to do. But this, for this portion over here, it doesn't matter. So that's why in thermal, we always like to try and do things in terms of U, S, and H. But for work, it does matter the path because of the second law. And we'll touch on this again throughout the class, so it's a good question. One last thing that I want to talk about with the closed rigid system here. Well, the closed, so if we get rid of the rigid criteria and we say it's closed, if we look at the energy balance in an integral form, right, this is the differential form, the rate of change after we've integrated, this is the integral form. If we rewrite the work as volume expansion work, and that's how much work it takes for the piston cylinder device to push back the atmosphere at pressure P. What we'll oftentimes do is we'll move this to the other side of the equation. So we have the change in internal energy plus the change in PV is equal to the heat required to accomplish the process. Then we'll oftentimes just do this. So even though it's a closed system, you still are using enthalpy. Right, so that's why I don't want people to think, oh, it's closed, that means you use internal energy. Oh, it's open, that means you use enthalpy. It's all just a consequence of the energy balances. So enthalpy is useful in more ways than just for open systems. That's sort of my last pitch on that. Okay, if we're going to do, let's do an open system, but let's say it is rigid as well because PV is kind of annoying. In this case, we'll only have one in and out stream. This is just to show another simplification. And also steady state. So lots of assumptions on this one here. But this is going to be the most typical scenario that you will see in a simplified industrial process. The only difference for more complicated ones is you'll have multiple in and out streams. So if we have an in and out, we have heat, we have work. Let's write out our general balance equation again. shaft work to make it clear that it's not PV work. All right, what am I approximating here? What am I getting rid of based on these assumptions?
That's 0, which is steady state.
Yeah, so this is all equal to 0. I only have one in and out stream, so I'll say that it's the mass flow rate in, the enthalpy in minus the mass flow rate out, the enthalpy flowing out, plus heat plus work. Now let's just say hypothetically for this particular example, we're trying to figure out how much power we can pull out of a high pressure, high temperature system in a turbine. So in that case, I don't know why it does this. I have like a series of like voodoo tricks that I try and make sure that it doesn't stop in the middle. I reset it, I turn it onto airplane mode, I disconnect it from Wi-Fi, I do not disturb. Sometimes it works and sometimes it doesn't, but I caught it that time. So there's no, when I stitch them together, I'm not going to miss out any material. Okay, so going back to the example, this is our energy balance. So if we say that we have a furnace that's producing high pressure, high temperature steam at some temperature and pressure, right, we can look up the enthalpy of that steam in the steam tables. We know what is the energy of it leaving. We can look up the enthalpy from the temperature and pressure of it leaving, and then we can directly just calculate the work by manipulating this equation here. Right? Pretty straightforward. More or less just algebra, actually. Linear algebra. So oftentimes what we'll do, though, is you'll notice here that this is in minus out. I feel like a lot of times when we think about enthalpy, we think of out minus in. Now the reason for that is most generally we'll move these two to the other side. In this case, since there's only one in and out stream, I'm not going to call it mass in and mass out, I'll just call it mass. Enthalpy out minus enthalpy in is equal to the rate of work output or power generation. And again, oftentimes we'll then just call this M times the change in enthalpy is equal to the work that can be extracted. In this case here, the delta doesn't refer to final minus initial, it refers to out minus in. You can kind of do a connection by thinking about your reference though. The time-dependent one versus the steady state one. In the closed system here, there's nothing flowing in and out, so the system makes sense here like a piston cylinder device. We basically just draw a line around our fluid and say that's our system for the closed system. Here, our system is actual box with streams flowing in and out, so there's mass crossing the boundary. We could also basically solve this problem here, not by thinking of it as mass entering or leaving the boundary, but that we're just following a volume element of fluid as it travels through the system and magically expands. We can think of both of those as appropriate ways to solve this problem. So you can solve most all problems basically open or closed depending on how you want to do the reference. Now this is simple because it's only one stream in and one stream out. But if you had a more complicated process, right, you want to do the thermodynamic balance of an entire chemical plant, you'll have multiple streams in, multiple streams out. You won't be able to think about it that way. You'll have to solve it as an open system like this. Does that make sense? So what I want to highlight here, though, is basically just give me some culpability for why I'm not going to go through any power plant examples or piston cylinder devices. Because what we just put on the board right here in, 15 minutes worth of class, this is about the extent of complexity for those types of problems. If you have access to steam tables or some sort of other source of information that tells you the enthalpy, that's it. There's not much else we can do. Reacting systems get a little bit more complicated, but not too much more so. So with that, let's do a really quick example, and we will derive the Carnot cycle. Rather, you guys will derive the Carnot cycle. I've already done it. How do I draw this? Okay. So calculate for the Carnot cycle the efficiency which we define in this particular scenario as the rate of work output divided by the rate of heat input. Your tools are going to be an energy balance and an entropy balance, and we're going to assume this is a steady state process. and closed. So many of you probably know the answer, but I would like one of you to come up and actually do the balances when we have volunteers. We'll have one forced volunteer for the energy balance, one forced volunteer for the entropy balance.
Yeah, I can come.
For energy,
Yeah.
let's have you do energy balance. Oh, make careful we don't hit the.
It's reversible, right?
Oh yes, and reversible. All right, do us the honors for the energy balance. Looks good to me. So one more step to get it into, I think, a form that we're going to want to have is that the work output is just the balance of the heats going in and out of the process. All right, now the entropy balance is a bit more fun. So I'll give you guys, looks like the people are still working. So we'll do the entropy balance in a moment. I'm just going to write down the general entropy balance so that people are right. All right, so that's going to be our starting point to simplify. Just so we're clear.
What's the first?
Which one?
The summation of.
This is mass times the
Okay.
entropy of that stream. Entropy is extensive, so more fluid, more entropy. Oh, and one hint, we can have multiple of this term, multiple of this term, and everything. We're just accounting for the entropy. So if there's more than one heat stream in, then of course you're going to have more than one mechanism for the entropy to be transferred to the system. Who's got the entropy balance worked out?
Entropy balance.
I'll grab another volunteer. Thank you, though. No volunteers for the entropy balance. Okay, let's walk through this a little bit. What's our system? Can someone tell me what's my system here?
It's a build distance cylinder. Oh, never mind. I'm just thinking, I'm like more. It's a Carnot cycle, you said, right?
Yeah, this is the Carnot cycle right here.
Okay.
This is the magic system that we're trying to figure out what are the rules that govern this magic system here. So that's the system. So let's go to our entropy balance. Which terms go away?
The mass.
The
DT.
mass.
So mass goes away. There's nothing coming in here. What else goes away?
The S gen.
DT.
It's reversible, so we have no entropy being generated.
So it's.
And steady state, so this goes to 0 here.
So Q, Q, H,
So
over
Q, H,
H.
over T.
0 is equal to Q dot H. Fallout.
You don't take the work into account, right?
Nope.
Why that sigma ms goes away? Mass term?
Which one, sigma? Where's the sigma?
That summation of m into.
Oh, this one here? Because it's a closed system.
With no masses coming.
Correct. Right, so this is kind of, we have a furnace that is providing energy to some magical process that is then somehow producing work. Now, if we didn't have this cold reservoir, this is one of, I think this is Kelvin and Planck's violation of the second law, right? You can, due to the directionality of entropy, you can never take heat and turn it into work. Work can only get converted into heat. All right, so does anyone know how to put the rest of this together? So we have work in this equation and QH in those equations. So put them together and see if you can rearrange it into this formula. Yep. Who's got it?
Is there any specific form you want us to get to?
There's a classical form that people like to do, but so what I'll put up the answer and then I'll allow someone to sort of put it all together. So the efficiency is going to be equal to 1 minus TC. Hopefully that'll give everyone the push that they need to connect those dots.
And make sure that what I got is the same thing.
Is that the same efficiency that's over on the right here?
Yes. This is equal to this should be familiar to everyone, right? This looks as expected. Okay, do we have a volunteer who wants to walk us through the derivation?
I need a second.
Okay, come on up. Now you have the answer, you're like, okay, I see it.
Recorded forever.
There you go.
Screw it up.
So how did we get there?
Because this is this.
Mm-hmm.
Let's simplify this a bit.
Masterfully done. Thank you very much. All right. Now we're done basically with energy and entropy balances in this form. Okay, questions? So to recap, we've played around with a little bit of energy and entropy balances. This again is one of those exceptions where we actually are playing with this heat transfer over temperature. But in general, for real processes, we will design basically all of our problems to always avoid this at all humanly possible, right? In the real world, we have to heat stuff up by actually having a temperature gradient, right? Heat only goes from hot to cold. So in the real world, when you want to design a process, you need to know what's the temperature gradient need to be between the two sides of my heat exchanger fluids, right? And there's heuristics in chemical engineering. If it's 500 degrees, it want to be a gradient of at least 100. If you want to heat it up to 50 degrees, you need a gradient of at least 5 or something like that. I don't design processes, so I don't know the heuristics quite well. But in real process, we'll always try and avoid this. But I guarantee that on the first exam, any entropy generation question that I'll ask, people will default to this one right here. So on rare occasions, yes. But if you find yourself going back to Q over T, really ask yourself, is this the way I need to solve the problem? In general, it's not. Okay. All right. So in terms of solving energy balances for real processes, this basically concludes the amount of material that I will spend on it. But that's not to say that energy balances and entropy balances are not going to be the basis for what we are working on, but they are almost always going to be a closed system with some sort of arbitrary confinement or constraints. And we will use those to track how the properties of fluids change as a function of temperature, pressure, density, and so on. So the way that we're going to think about it now is our system, from here on out more or less, is going to be with the objective of tracking and predicting fluid properties and phase equilibrium. That is going to be our objective. So our system is going to be an arbitrary volume element of fluid that we're magically going to transform from one temperature and pressure to another temperature and pressure. No rules about how we're going to do this. It's just going to be basically a magic box that we can just magically transform the properties of this fluid. And the boundary of the box is going to be some arbitrary line that we draw, and so that's the way that we're going to think about our systems from here on out. So, in that vein, we are going to derive the Helmholtz and the Gibbs energy. These are definitions. They're just made up functions that happen to be super useful. So how we'll do it is for Helmholtz, our system is going to be closed, isothermal, and rigid. So in terms of thermodynamics and statistical mechanics, this defines what we call our ensemble. This is how we're doing our calculation. N, V, T, N meaning constant number of particles or moles, V meaning constant volume, it's a rigid walled system, and T meaning that it's going to be isothermal. Right, so how, which variables you hold constant determine how you're going to perform a calculation. Right, so this is the NVT ensemble. So I'll kind of go through quickly the balances here. So in this case, our energy balance is simply the change in internal energy is just the change in heat and the change in work. Since it's closed, we don't have any mass flowing in, there's no enthalpy to worry about. Our entropy balance So what we'll do here is basically we're going to combine the first law and second law of thermodynamics, very similar to what we did for the Carnot cycle efficiency. So in this case, we will write this as heat is equal to let's see. Substituted into the first law. Let's see, oh, yeah. So work is going to be equal to, I just want to make sure I have my sign convention correct. Let's see. We will actually, not quite. We're going to use this here and define the Helmholtz energy. Oh, sorry, delta A is defined as delta U minus T delta S. So this is if the rate of entropy generation is equal to 0, which means it is reversible. So let everyone write this down before we talk about it for a second. Okay, so the Helmholtz energy, most oftentimes in thermodynamic classes for undergraduate, is described as the reversible work that can be extracted from a closed isothermal system. And that's how, in fact, we derive it. In practice, for what we're going to be using it for, actually we won't use it very much. What it's used for in more general chemical engineering thermodynamics discussions is it is used for phase equilibrium in liquid systems. Is the most general application of the Helmholtz energy. Because in a liquid system, we oftentimes will view it as an incompressible fluid, so there's no need to add in the extra complexity of PV or pressure volume changes. In chemical engineering, we are most interested in, most of the times, vapor-liquid phase transitions for distillation. So that's why we don't generally use the Helmholtz energy, we more generally use the Gibbs energy, which we can derive in just a second. Now, when we derive it including entropy generation, this contribution here is the reversible work. Here we're adding this TS gen, temperature times the rate of entropy generation. However, in this case we've defined work as positive going into the system, so negative work is the work that we want to get out. So having this positive term here basically means that when you generate entropy, you are always going to be having less work coming out of the system. So another way to write this then is that the work that we can get out of the system is going to be the reversible work plus this T times the entropy generation. In this case, negative work is out of system. So when this is more positive, that means you're getting less work out of the system. At least the objective is what we're trying to accomplish. Next, we'll do the Gibbs energy. We'll do it really quickly because it's more or less exactly the same procedure with a little bit of trick to it. So in the case of Gibbs, this is going to be isothermal, closed, and isobaric. So in this case we have T, N, and P. We write this though as NPT. That's our ensemble we're performing this calculation in. And for our purposes as chemical engineers, most generally NPT is the most convenient because they're the easiest functions to measure, temperature and pressure, right? Because we don't have an internal energy gauge that we can just slap on the side of a tank. We can very trivially with a thermocouple or a pressure gauge measure temperature and pressure. So for controls purposes, that's why we like controlling pressure and temperature. So if you write out our energy balance, in this case, the change in internal energy of our system here, heat, shaft work, so this would be our turbine, PV work, this is the entire unit operation, expanding and contracting, pushing back the atmosphere. So the only difference between the Helmholtz derivation and the Gibbs derivation is that we take this term here, move it to the left-hand side, change in internal energy plus pressure volume. This is the definition of enthalpy. If we take exactly the same entropy balance, because the entropy balance is going to be identical, we can define the Gibbs free energy as enthalpy minus T delta S, temperature times entropy change. The same logic applies here as well, that the Gibbs free energy, from a sort of process engineering perspective, can be viewed as the reversible work that can be extracted from a constant temperature, constant pressure process. But what we're going to be using it for is not for anything like that. We're going to be using it for phase equilibrium, because as it turns out, going across a phase, the Gibbs free energy is held constant. So many times we'll refer to the Gibbs and the Helmholtz as something called the free energy. Right? It's the excess energy that can be extracted from the system, sort of the coherent energy, not just random motion of the fluid. So the next step, though, in phase equilibrium that we'll talk about, maybe not next week, but the week after, is fugacity. So the problem with the Gibbs free energy is actually in this entropy term. When you have a multi-component, multi-phase system, entropy becomes a little bit tricky. What happens in the real world, everything we're assuming is infinite in thermodynamics. So what that means is that if I have a mixture now, and I have a mixture of pure A, and I want to make a multi-component mixture. So I want to know what is the entropy change when I mix two fluids together. The challenge here, though, is that if I put a droplet of B inside of A, what I've done is I've now given B molecules effectively an infinite volume to move around in an infinite sea of A. So the rate of change of entropy of fluid B actually becomes infinite when I do a dilute system mixture. That leads to a discontinuity in our mathematics, which means that the Gibbs free energy is kind of a pain to work with. So instead, people in thermodynamics came up with a clever solution. They say, you know what? Let's not worry about the Gibbs energy or the absolute value of Gibbs energy. Let's calculate the Gibbs free energy relative to an ideal gas. Because an ideal gas has this problem, where when you mix them together, the rate of entropy generation is infinite. So the whole purpose behind fugacity is really just a mathematical trick in order to allow us to make phase equilibrium calculations easier. Who remembers the term fugacity? Okay, good. So no one really knows what it is, right? It doesn't really have a physical meaning or understanding. The reason why we define fugacity, and we'll talk about this moving forward, but I want to sort of just plant the seeds of it right now, is because of some mathematical trickery with respect to entropy. So, more entropy discussion. More entropy discussion than you thought you'd ever have in your lives. Let's talk about entropy generation. What is it? How does it happen? So to do this again, we're going to go back to our arbitrarily defined systems that don't exist in the real world, but they are very useful for us to understand fundamental chemical physics. In this case, we're going to have two chambers, A and B. They could be the same material, they could not be, it doesn't really matter in this scenario. This box is completely isolated from the rest of the world, or it's the entire universe. It depends on how you want to think about the problem. So this is a completely isolated, rigid box. Nothing goes in or out except, actually no, nothing goes in and out. No energy, no work, nothing. So in this case, the difference between A and B, and we're going to say it's a different temperature. So I'm going to define heat as going from chamber A to chamber B. One additional assumption, chamber A is well mixed and chamber B is well mixed. Now what that means is that the rate of heat transfer is much, much slower than the rate of heat transfer internally. So in this case, what we're going to say is that Q, the rate of heat transfer, is going to be equal to minus some thermal, heat transfer coefficient, oh, there we go, got it out, multiplied by the temperature difference between these two reservoirs. So we're just going to say that this H value, this thermal conductivity or heat transfer coefficient, is very, very small. And you'll see why we have to make that assumption. So let's start off with an entropy balance on side A. So the rate of change of entropy of side A is going to be equal to the rate of heat transfer right? This is just our closed system entropy balance. The only difference here is that we don't have the mass flowing in or out. Because this is well mixed, and this is cyclic logic, but just bear with me for a moment, we're going to say that the rate of entropy generation on the inside is 0. The conclusion of this derivation will show us why we can say that. Okay, so it's a little cyclic. Substitute in our definition for how heat is being transferred. We have minus H. Mistakes, good. We'll repeat the same process, but in this case on side B. The rate of entropy change on side B is going to be equal to virtually the same thing, but in this case, oh, I'm sorry, minus, plus. Okay, I know how I have it written on my paper here for my notes. But I think I actually drew my drawing wrong. So my notes have it like this, so I think that means that I'm defining my Q as positive this way. So I think my drawing is wrong. Because we're looking at a balance on A and Q is positive. Yeah, so my drawing is wrong. I update my notes. So the entropy balance on B is going to be, substitute this in. All right, we're on track.
Is it Q dot?
Yes, sorry. Now we're going to do an entropy balance on the total universe. Now this is almost always the way that we're going to solve for the rate of entropy generation. This same procedure here. Do a balance on one system, do a balance on another system, and then do a total balance. So anytime I ask you to do an entropy generated question, this is virtually always going to be the way that we're going to do it. I don't know how many times I can say this, but I guarantee one of you will still try and solve Q over T on the exam. So the rate of change of entropy of the whole system is just the rate of change of entropy, A plus the rate of change of entropy of B, which is also equal to how our system is interacting with the surrounding universe. In this case, there is no energy exchanged with the universe of the total system. It's only moving inside these chambers. But in this case here, we're not going to assume that there's no entropy generation. So what I'm going to do is I'm going to substitute in our balances for the A side and the B side into our expression here. So it is just going to be minus H. So those of you who are really good with your factoring, going all the way back to, I don't know, what is that? Algebra 2. I'm not.
Shouldn't one be TA and the other TB?
Oh, yes, sorry. Okay. So if we cross multiply, rearrange, factor, all that stuff, this is actually equal to if we worked out the algebra for a little bit. And I'll write this as a simplified notation. And our final conclusion is here. These are our two takeaways. Give everyone a second before we talk about the implications of this.
The lowercase h is the convective heat transfer coefficient, right?
Yeah, not necessarily convective, just some heat transfer coefficient. I don't want to necessarily ascribe any particular mechanism to it. So, what this means, and this is something to keep in mind for all of the universe. Anytime we have any gradient, entropy is being generated. This is what the conclusion of this one here is. Now, we did this based on temperature because temperature is a really nice, easy one to demonstrate. But it's appropriate for every system. And this goes back to the question that was asked earlier about the time scale. So, if I have a pot of water, right, this is always my classic example. I like pasta a lot, so that's the example that I always use. So I'm trying to make pasta or maybe making noodles, I don't know. However you want to describe it. And we have a flame. On one of them we've got a big flame, and the other one we've got a small flame. The objective is to boil each of these pots of water. Which of these two is the most energy efficient way to boil the water?
Slow one.
The slow one. Why? Smaller gradient, exactly. So anytime we're trying to heat something up, if we want to do it quickly, we have to pay an entropy penalty. The larger the gradient we have, the larger the rate of entropy generation. So that's also why, when you have a heat exchanger, which of these two designs is better? Co-current or counter-current flow? So if I have co-current, I have two streams flowing in and out versus countercurrent, where I have one stream flowing one direction and the other flowing the opposite. Right, why is countercurrent the more energy efficient way to do it?
So at every point, the gradient will be smaller than in the co-current.
Exactly. So from a thermodynamic perspective, countercurrent is the way to go, always. Same reason why, if we have a piston cylinder device, I'm trying to find any blank space we've got here. I'm expanding my piston cylinder device. Let's say I instantly expand from here to here. Boom. What I've done is I've created a pressure gradient internally and a pressure gradient externally because I'm locally pressurizing the air right on the other side of it that then has to push its way back throughout the rest of the atmosphere. So when I expand something rapidly, I'm creating a pressure gradient, which is wasting energy. So the only way that I could ever do anything reversibly is if I do it infinitely slow, which basically means that I have to heat anything up or pressurize anything in infinitely small increments. So in the case of a heat exchanger, right? If I'm trying to design one, I maybe want a 50 degree C temperature gradient because I know that I can't have an infinitely long heat exchanger. So, but if I want to do this reversibly, my temperature gradient could only be maybe 0.001 degrees Celsius. That would result in a very large heat exchanger, which costs money for copper, for steel, for just space that it has to be occupied in. So that's the engineering decision that has to be made. How much energy do you want to throw away when you go about and do these things? Now, generally, people don't concern themselves about entropy too much when they're designing heat exchangers, but that's the principle that underlies all of this. So, if I am mixing two fluids together, I'm always generating entropy as well because I have a gradient in chemical composition. So when molecules diffuse, when A diffuses into B, that causes entropy to generate because of the mixing. The mixing process and also the fact that you have a gradient in the chemical potential. So everything that has a gradient generates entropy. Now this example here is just nice to illustrate because it involves temperature, but we can demonstrate it for all the other ones. But that holds true. How is entropy generated? By gradients. Anytime there's a gradient, entropy is being generated. So we're out of time. Any questions? Yes?
How the counter is more energy efficient?
Was that?
Why the counter is
Oh,
more
right. So let's say, for example, let's just hypothetically say that this is at 100 and this is at 0, and then at the end, we want them all to be 50-50. So in this case here, our gradient is 100 degrees C, this one is nothing. So if we do it opposite, if we say this one is 50, and this one is 0, and this one is 100, okay, sorry,
50.
This is 50, yeah. 50, and this one is,
No, yeah,
No,
you're.
no, wait, yeah.
100 exit 50.
This one has to be 50, this one has to be 100, okay, yeah. I'm just flipping the bottom string. So in this case then, the gradient here is 100 degrees, 100 squared is substantial. In this case, the gradient is always 50 degrees, 50 squared is less than 100 squared. We're still generating entropy in both of these heat exchangers, but we're generating more entropy here. So from an energy balance and an entropy balance perspective, I think also energy balance, it makes sense to do countercurrent too. But entropy does also. All right. Noon, barbecue, hope to see you all there, and have a good weekend. See you on Monday.